Discord. Yeah, let's start. Thanks for coming. So, okay, chapter 7 again. Okay, let's go to one section by one section. So yeah, circuit compilers. Yeah, let's start from this. So pen and paper language questions. 7.1.1. Grammar. Any questions? We'll come back again later if you have any questions as well. Um, Execution phases, setup, and approval phase. In this case, you are free to ask questions in chat, or you can just raise your hand and ask with a voice as well. Questions, approval phase, and now we are at real world circuit languages. Circom. Questions? No. Okay, while you think about questions, let's go through a little bit of the important stuff here. So yeah, 7.1. Here we talk about pen and paper language. So looking what's here, we can see that this is written, and this looks very complex, but actually it's very simple. What it's essentially it's a descriptor of grammar for a language. In this case, a circuit language, but in general, programming language as well. It will look something like this. So statement name. This name is just something that you give. This is the parameters, field, and more. This just means that it can have multiple field. I think this is a statement actually. Yeah, sorry. Yeah, I have unfortunately got this wrong. So it defines the statement, any statement in language, as a name that has in the format of this field. So F field, N1 unsigned, these are all the types. A function. This is also considered a statement, I believe. Yep. A assignment. Both are assignment, but one is just an assignment for a variable, one is an assignment for constant. Um, so this specifically, I believe, let me take a look. Where is this? Yeah, the curly brackets are pretty hard to see. Let's see. Yeah, so statement name, field. So this describe, I believe this is a declaration. Yep. And this is describing, hey, a statement can be a function as well. I think it's here. And this is, oh my God, the curly brackets. So within a function name, within its parameters, can have a public modifier, and then it can have many arguments types. So this just means, let me see if I can show you. Let me just get something real quick. Give me a moment. And let's see. Okay. Oh, give me a moment. There you go. Okay, great, 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 great. Oh, oh. Let me just take this and beautiful. And let me just set this into Rust because I usually okay. So what this means, it's just saying that, hey, I can have a function of some name, some function. Okay, I'm talking about this specific um line, this specific line. Um, okay. Excuse me. Uh, in a function, it can define as some name. So this is the name, and within its arguments, it can or cannot, it might or might not have this part keyword. Okay, but the arguments will be in the form of args, some type. Let's do U32. Why not? And you can have multiple of this, right? You can also have an arg2 that is a U256, whatever, right? And then it will have a return. So this is a return, and in this return, it can consist of it will be actually in this case actually defines it as a tuple that returns some type you define. Again, you can put it as U32 or whatnot. So this just means that here, for each type here, you can have a pub, right? The pub means this, right? You can have this. If you don't put if you do not put in pub, it's not public essentially, right? Because remember our previous chapter we talked about public and private variables, or in this case instances and witnesses, right? So yeah, this just defines the syntax to be like, yeah, we accept this syntax. And if you look at the curly bracket here, right? This curly bracket simply means within this function, um, you can have an assignment like assignments. You can have, I believe this is a constraint, some variable that is another function. I think it's assigned to another function, or just arguments, constants, or variable. Yeah. So I think this is just a variable that is in a function that can also be pointing to a function, or like other variables or constant assignment. I believe that's what this is. Yeah, I believe that's what this is. So in this case, so there's also return. This is just saying that, yeah, each function will have a return, and the return we need to end with semicolon. Actually, each statement here needs to end with a semicolon. Yeah. So I don't think, is this a complete description? But yeah, I don't know. But anyways, yeah, what this means is just saying that, yeah, some stuff are possible, and what's how the language might look like. In this case, it actually looks quite a lot like Rust. But yeah, you might also see this if you look at other languages as well. Yeah, so grammar of a statement. Yeah, so this defines the what 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 a statement is in this particular paper language. Yeah. Yeah, they also define like there is a need for a mean function, and this mean function will also have the same time as a same constraint as the other functions. Yeah, that's essentially it. So this is what this means. Var is like component in circom, I guess, but can only do a single was. Yes. Oh yeah, you're right. Yeah, I accidentally interpreted this as a normal language. Yes. So it's a constraint. So this defines a actual constraint. We also talked about that in our previous chapter. An actual constraint of some variable to another variable. What's a constraint? Just to remind you, is essentially some things that we want to check. It's a in this case, I believe it's equality, but of two different variables. F1 and N1 inside. Not necessarily. I don't think this is template. A template can be a template. It's more like a function in Circom, I believe. So this is not Circom. One correction is this is not Circom. This is another language that we're talking about. Circom has another different set of grammar. If you look at Circom, there is a statement that is defined in terms of name. I do not think this is a template. Template parameter. I don't think so, but yeah, I might be wrong. Yeah. Um, yes, yes. Let's look at some example. So here, yeah, the author say it is inspired by Circom. Yes. Oh yeah, 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 you're right. Sorry. Yeah, I got it wrong. Yeah, because Circom I think uses um what's that called? Another bracket. Yeah, yeah, you're wrong. You're right. Sorry, you're right. Yeah, in this case, it is the template style. But I believe yeah, yeah, it's a template style. Yes. So essentially, this defines how the language will look like. So yeah, don't worry too much about this. If you find this intimidating, yeah. Oh, you're right. You're right. ZK, by the way. Yeah. Yeah, I'm not very used to this. Yeah, I was wrong. Anyways, okay, so this is how it looks like. The language, for those they are familiar with Circom, this is essentially the template. Yes. Um, and yeah, so one thing that you'll notice is why separate the function and the function main is because the function main here, we essentially want the language to always have a main function in a statement. So it means that if you take away this, you will have if you're a programmer, you will see a syntax error. If you take this away, because it doesn't fit the language, right? You must have a main function. But yeah. So yeah, this is how an example pen or paper language can be. And this is designed so that you can down here, it actually talks about how we can convert this into a circuit. And one thing you might ask, so where this actually also mentioned, why do we need circuit compilers? Well, it's because it's very hard for anyone to convert your programs into rank one constraint system or algebraic circuit straight away. Let's say I give you some program that does power of two, for example. If you want to convert that into a circuit and then write that into you need to write a program that processes that circuit. It's not easy, right? It's not an easy task. That's why we have circuit compilers. Circuit compilers allow us to write circuits or programs relatively easily, while the circuit compiler itself does the work of converting those circuit or programs into R1CS for us. So that's why we need it. That's why like programming languages, like no, sorry, circuit languages like Circom, Alio, um, Cairo, Noir exist. It's because we we need to, yeah, it helps us write a program easily, a ZK friendly program, or like a program that we want to ZKify a lot easier. That's why also there's this saying of a programmable cryptography, where you can essentially program your own cryptography using ZK. Yeah, fun stuff. Yeah, that's why we are interested in circuit compilers. Okay, see you're immediately hopping into grammar. Are we skipping the token definition because inspired by circumsocrates? Do we need to define as tokens for circuit compilers? Okay, if you implement it, yes. If you are actually implementing this into an actual compiler, you do need to define what each token means, right? You need to define what tokens that exist, and you also need to define the behavior or like the keywords for like what's the okay, what when you define a token, you define um what the tokens are, like what keywords they are consist of. You also need to deal with parsing the string into a token and so on. You also have to um, define what each token do. In this case, they don't necessarily define, but they do define, right? If you look here, the token, like this is a keyword argument, right? This is a statement token. This is a identifier token. This is I guess parameters, right? And each parameters we can define them as a token, right? The function keyword, this is a token, identifier token, parameters, return, return keyword, variable, this is also an identifier, and then this is the assignment, in this case is a assign and constrain token, and this is like what's behind it, right? Technically, we are defining the tokens here. So we are defining that they are the identifier, in this case, we call it name token, the var token, the type token, the cons token, which is essentially just var, but with this, right? And the keywords, right? Let cons, return, and this is also a token, by the way. This, right? Actually, but depending on this, you have to actually analyze to know that this is part of the statement. Yeah, so we do actually are defining tokens here, if that's what you mean. It's actually defined here. But yeah, in a actual compiler implementation, you do need to, well, it's not just, we cannot just put this in and expect the compiler to understand, right? Or like, we can't just have this and program something that just generally detects this. We have to actually deal with detecting or converting raw strings into tokens, and then um, converting the bunch of, like, the arrays, the bunch of tokens into abstract syntax tree, yada yada. Yeah. That's when you want to implement the compiler. But yeah, so in this case, they don't actually put, like, separate this entire thing out and say what tokens are there, but they are actually defining the tokens indirectly. They don't talk about, like, yeah, name token is an identifier and whatnot, but they are defining it in this form. We are defining the grammar. I hope that answers your questions. Yeah. We are not skipping the token definition because I mean, I kind of is, but it's not technically skipping it, because these are the formal definition. Yeah. This is defining what token is. Anything with this angle brackets, those are formal token. Oh, this is actually also a token, but yeah, anyways, excuse me. Yeah, good question, by the way. Yeah, if you are interested in implementing a compiler, you don't necessarily need to write something like this out, but this does help um people understand grammar. Yeah, when I do it, I don't write this out, by the way. I just implement I write an example program and I implement the grammar. But yeah, writing this out does help you define your grammar in a more formal way. Mm. Okay, anyways, let's go into the grammar. So execution phases. Yeah, so please do ask any questions again. So in execution phases, here we separate out to setup and prover, and the difference is simply that setup, we are basically converting this circuit, you see here. So this is an example. This circuit, let's look at the circuit, right? So some circuit, we accept, this is defined, sorry, we define a circuit to have a field of 13, order 13. And we define the main function to accept input 1 and input 2. Both are type of field, so this field, and return two values. And we define two constants, type of the field, 0 and 7, two output, both type of the field. And then we just assign and constrain this constant to the first output, first input to the second output, and the constant output is constrained to the second input. This is a little bit confusing if you are used to programming languages, because this is a constant. It shouldn't be able to be changed. But alas, I also am not quite sure why they don't define this as a simple variable in this specific case. Might just be my understanding of constants is wrong. It's been a while since I wrote Circom and Zocrit, so maybe they do allow this. Yeah, anyways. And then we return output 1 and output 2. So what the compiler will do, or in this case, during the setup phase, is it will actually convert this into a algebraic circuit or an R1CS for the later stage. So yeah, so for this specific pen and paper example, what we're doing is essentially we're just saying, yeah, input is this, witness 1. So when we do this constraint, we constrain input 1 to output 2. There is a constraint disassignment process, I guess. this is just the value of the input witness one. And then we again put our inputs 2 into the constant, which is not outputted, by the way. So we don't really need, like, this doesn't really matter. And then it does matter actually in this case because it's a constraint. So we have to constrain input 2 to this. In this case, I think this might be just a simple comparison constraint. So we are constraining input 2 with this. So input 2 must be 0, does this. And then we also constrain output 1 to 7. Yeah, so this is the result of the result of compiling this. In this case, our brain, right? Yeah. So they actually describe what this does, right? So this is an assignment operator for them. That's really weird. But yeah, this is an assignment operator for them. So in this case, yeah. So yeah, that's what in the setup phase things happen, right? Let's look at what they talk about when we talk about the setup phase. So in this case, yeah, we are brain compiling problem. We are just computing this ourselves, looking at this program. But generally, well, the setup state, what it does is so here, given some statement description that adheres to correct grammar, we start compilation. So we'll empty circuit, compiling main function first, and inductively compile all the functions. And so this just describe how it's done. I want to look at what it's actually doing. So if you look at I believe here, yep. So the setup phase is executed in order to generate the circuit and its associated rank 1 constraint system. So the circuit usually is convertible to an R1CS, and then so the rank 1 constraint system can later be used by a ZKP system to be used for generating proof and verifying proof. So in a ZKP system, we'll cover this later, but in a ZKP system, usually that's also a setup stage. But the setup stage is different from this setup stage. In the ZKP, you would have a prover and a verifier, and both of them require your associated R1CS to essentially compute essentially it will use this to compute or to create a proof or generate proof or to compute if your proof is correct. So this is like a important thing, right? And this is essentially a polynomial. Yeah. Yeah. So if it's confusing for you, just remember that we need this. Actually, in the previous chapter we talked about this. But yeah, we need this so that we can actually prove our statement, or we can actually prove our program in this case. Or we can actually use ZKP on our program. Yeah, I think that's a more accurate way of saying it. So the second one of execution is called prover. So the prover phase, assignment to all instance variable is given as input, and the task of prover is to compute valid assignment to all witness variable of the circuit. So depending on the use case, this valid assignment is either used as a constructive proof for prover circuit or transferred as input to the proof generation algorithm. So you might use this. So this might be done together with the proof generation stage, where you generate the proof. So let's go back here. So yeah, that's what essentially. So the setup phase, what we are talking about here, is essentially converting this statement into this circuit, which in turn becomes an R1CS, right? Recall R1CS being in the form of A times B minus C, or A times B equals C, right? So in this, we can make it into multiple statements, which is in that form. Let's do a quick revision. So we can convert it into something like this, right? So for example, we want to convert into some form like this. For example, let's see. The example is I can't find it yet. Yep, here. I think it's here. So this is last chapter, by the way. So yeah, this is one of the examples, but essentially we want to convert all statements into multiple statements like this. So this is R1CS, and this is actually very easily convertible into a circuit. When we look at, this is like an example, right? F3 F equals x1 times x2 times x3, and you can convert this into a circuit if you break it down. That's why when we talk about circuit, it's usually very much convertible into like an R1C as well. They are very easily yeah converted. Anyways, yeah, there we go. So setup phase, yeah, that's why in the end we see this, right? And this is converted into an R1CS. In this case, you can convert this into like what? You can think about this as yeah, you can convert this to an R1CS. R1. So A times B minus C. Yeah, this does not have any minus, but you can probably evaluate it line by line and just put like what B is 1, and in this case A would be out 1 equals C inc 1, and the same goes to the A times 1 equals C. A times 1 equals C. So essentially the statement would be, you know what, let's try, right? Let's try. Let's try. So if you want to convert this into R1CS, it will be along the lines of so let's look at only the constraints, right? Because that's the important part. So S, okay. Let's just mark this as S. Okay. Out 1, right? Let's convert this to R1CS. We recall R1 is A times B minus C, and we want to convert all of this into R1CS. So it's O1 times 1, B will be 1. So we assign the values here, right? And minus C, so equals, I mean, in this case, we don't minus C, just to equal C. Because if it's minus C, it will be minus C equals 0. So it will be A times minus C equals 0. So this is R1CS. It's the same thing as A times B equals C. So in this case, O1 times 1 equals, let's do this as C what? C what? No. Oh, it's bad. Yeah, sure. C1, and then again, this is the same thing. O2 times 1 equals I1. Let's just call this I1, this input, and O3 times 1 equals in this case I2, right? And then yeah, this is essentially our R1CS for this specific program. Yeah, which is, well, a very simple one because it's a trivial circuit, but a more complex example would not just be like this, right? Yeah, this is just an example. And this is very easily, well, if you, let me just clear everything. Right? Oh, okay. So if you look here, yeah, it's essentially, well, if you look at this, it's very easy for you to convert this into statement, this into statement, and this into statement. It's not that difficult. Yeah. So yeah, that's fine. Okay, anyways, that's the setup phase. And so in the proof phase, they don't go deep into this. But in the proof phase, what will happen actually is just that essentially, given all these instance variables, so in this case, actually, we don't have too much witnesses here. But if you were want to say like there is a witness, right? The witness here, actually, there's no witness here. It's pretty sad. I mean, I guess we can call this a witness. Yeah, I guess we can call this a witness in this case. But in the prover phase, yeah, we have to essentially compute witnesses based on the instance that was provided. So in this case, the instance provided is in1, in2, and in3. And all the intermediate steps, we have to compute the witness and get yeah, and essentially get some output, right? That's the prover phase. So here it actually talks about like, hey, in a so-called prover phase, the executor while assigning profile values to all input nodes. And yeah, in this case, the input values are, well, they are not really, well, in this case, because this is a pen and paper example, they don't tell you like, hey, your input is taken from where. And so yeah, you can't really do the proof of phase here. But yeah, some computation can be done actually outside of the circuit and then input into this. And yeah, you will use that as an input and compute all the witnesses and then yeah, do an execution of this. Yeah. Anyways, yeah, so the proof phase, so this essentially also usually would be done with the actual proof generation, where you give it some specific input that you want for your specific ZKP. So, the ZK application, and it will just go through this, attempt to execute it, and then find out all the witnesses and then generate a proof together. But in this case, the proof of phase is it doesn't really, in this pen and paper example, it doesn't really show it that well. That they have a separation between the setup and proof of phase, but essentially it's again one of the execution of, it's once again an execution of your circuit, but in this case with the actual input that you want to use. In your setup phase, if you use in your setup phase, usually you will use some input as well that you provide. But the inputs that you provide in your setup phase might be it might be inputs that you, how do I put this? It might be inputs that you are using just to verify if your circuit is correctly written in a way. Yeah. If you do use circom, you might remember that as you have to put in some input when you compile your circuit or when you start setting up your circuit and all that. That's one of the reasons it helps the compiler verify if your program is correct, if I understood this section correctly. Yeah. Okay, anyways, let's go into 7.2. Any questions? So 7.2 is actually pretty simple. It's just talking about circom and multiplier. So implement 3 factorization problem, which is the example in the previous chapter. And it looks like this, right? The template thing, it's essentially you're right. ZK, it's essentially the statement thing in the previous section. And here component, get this, and then this is a little bit weird, but essentially what this is doing is I am defining there's 3 input and 1 output. And so this doesn't say actually that if the inputs are public or private. In this case, they should be all private because you don't mark them. I believe circom, you have to mark them to be public to be public. But anyways, and then you create 2 components which you then use to multiply things together. And here, all these are considered a constraint assignment. And after that, you just assign your result to X4, and then this is automatically the output. So essentially it's a very simple language just for writing circuits. And so a little bit of a bonus. Let's look at actual circom code. So here essentially it is, right? So this is how it looks like. And so in circom, there's also a component main here that you actually define in order to say that what your inputs are public. You can also change this, right, to just why it doesn't tag my, oh god, okay, never mind. You can also put B, you can also put A, you can make both of them public, right, which defeats the point. But anyways, so in this case, if you look here, the yellow stuff is just saying that this is unused and there are not really used. And so this essentially is let's look at this, right? Let's look at this example program that they provided us very kindly. So A, B are input, and then the C, we multiply A by B, assert A is more than 2, and then that's it. Hash input, this is a hash. We don't really care about this. So this is essentially that. Here you can see like there's a Poseidon hash component. And if you run this, let's shift enter to run. If you run this, it works, right? It is telling you there's 1 public input, correct? 1 private input, correct? And there's no private output. Wait, I never knew there can be private output actually. Well, today I learned. Anyways, and it's telling me that the output is 385 given my input. So this is during the setup stage, right? Set up this, convert this to RNCS, and you get all this, right? See? This is ran during the setup stage. In the prover stage, we might need to put in we actually will need to use all this information to actually use like generate a prover or start using it as a prover. But yeah, this is used during the compilation stage. It just compiles into R1CS and just tells and just prepares it for later on when we actually want to use it as a proof. Yeah. Anyways, so can I verify it? Oh, wait, what is this? Oh, no, 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 no. I think I will. There is I think I can just do graph. There you go. So oh, the hell. Nope, it doesn't work anymore. I forgot how to actually. Oh, there you go. There you go. So in this case, again, so you can also, this is a demo, right? So you can generate proof here, and this is a proof. As you can see, it looks like this. And you can verify it. Proof is valid. If let's say let's change, I think we can change this. So okay, again, you see 3, 8, 5, and 5, because remember 5 is public, a public input. And but if you change this, let's say when you do verify, you do need to put in your public input. When you change this, yeah, it'll be invalid, right? The output is also considered a public instance in this case. So yeah, interesting thing to know. Anyways, that's what it is. That's how it looks like in the real world scenario. Of course, in a real world scenario, you also usually will pair this with let's say Solidity contract as a verifier, and the proof generation you will be usually done off chain or on your browser. Okay, so yeah, this is how essentially Circom will look like as well. Yeah, just a quick look. Could there be any mismatches in variables labeling when you set up improvers phase, creating any bugs? Um, Very interesting question you've asked. Um, I don't think so. The compiler shouldn't do this mistake, but I mean, I suppose if you introduce that bug, then yes. If you introduce the bug in your setup phase, in this case, or you introduce a bug to your compiler, and your compiler does different things during their setup and proof phase, then yeah, it can have a bug. But generally, no, not really. I don't think so. Okay, yeah. So that's essentially so what Circom is. It's quite popular, but yeah, now there's new language out there that's a little bit nicer to write in. But generally, they will do the same thing, right? They all do the same thing. Okay. Anyways, yeah. Any more question? Do ask. Okay, so yeah, that's what Circom is. So yeah, so please do ask any question. Yeah, 7.3. Any questions on 7.3? The 7.3 actually just talks about some general programming information, primitive types, control flow. How and where verifier public inputs are needed to improve verification if you look at the polynomials and parent check. Okay. How and where verifier public inputs are included improves verification. If looking at polynomials and parent checks. So the public input, well, this one we actually do need to. So we actually cover this in the next chapter. But essentially, these inputs or these instances, you need to plug them into essentially a polynomial that we need to check for equality, or in this case, I mean, not equality is the wrong word, I think. Yeah, you essentially you'll be given there is a polynomial that you use to check, and that polynomial itself you need to check if when given these inputs, when you plug in these values, um it holds, or it, I don't remember how it holds it, but yeah, essentially the inputs are well, they are used in the verification phase as a variable into the checks itself. And if you're talking about proof generation itself, um, they do the same thing, right? When you do proof generation, you generate multiple values, and those values are essentially part of the proof. And well, you might also want to pass your public input as part of the proof to be sent to whoever is trying to verify. And for the verifier side of things, um, you take your public input, you take your proof itself, and then when you verify them, you have to plug those values into check if your polynomials or if your equation holds. Um, well, maybe in pairing checks, and in this case, in pairing checks, if the 2 points are the same, right? Yeah, to put it insanely high level, I think. Um, if you want to go into detail, I think I'll go a little bit more into that next chapter. But essentially, yeah, I'm not sure if that answer your questions. Um, exactly where I put it, like where the values are placed into the polynomials itself, or in which step of the process, I'll need to do some revision before I can answer you that. But in general, it will be plugged into the check itself. So it's part of checking it. It's part of checking the proof itself. So it will be included in the equation itself. Um, yeah, not sure if that answer your questions exactly. Checks for FY or embedded in target module and some other polynomial and included only in fiat Sharpmule challenge. I do not think it's only included in fiat Sharpmule challenge. Um, check where evaluation of fx equals y or embedded into target polynomial. Um, I'm not exactly sure on this. Sorry. I don't think it's only included in the fiat Sharpmule challenge. I'll keep this in mind. I'll check it and I will come back to you. Okay. Anyways, let's come back to these. So, yeah, in common programming concept, this is essentially, yeah, how some of the concepts in non-programming language might be able to be used in circuit compilers or circuit languages. So yeah, any questions around this chapter? Does circum let the setup phase and the proof phase run together like them? Same code in paper, they are separate. What's is being gained or given up? Okay, so they are separating. Okay, I'll say this from what I've understood. They are separating here to provide clarity. Because the circuit compiler itself, at least for the circuit one, I believe, when they compile their circuits, you need to give them some sort of input, a valid input that they can use in order to generate R1CS. So it's just the inputs is not necessarily a production input like when you actually use it in real life. Um, it's some input that you use that you provide so that the compiler can understand or can go through and execute a circuit and generate an RLCS based on that. It's mainly for that. But when in the prover stage, from my understanding, in the prover phase, what it's actually doing is the real work. So, for example, when you let's say, so here, right, it generated R1CS, SIM, and this, right? These are all things that are important to the circuit. So these all represent the circuits, right? And in this stage, I'm just providing this value, right? It doesn't really matter what these are. I can change this. But let's say if I use it in production, let's say I deploy it somewhere, um, right? And after when I deploy it somewhere, okay, And I want to have a different value, right? I want, let's say, 113 and 10. Okay? And I generate the proof. So it's 130. So in this case, this will be the prover stage. In the book, they explicitly separate it. I am not the author, unfortunately, so I don't exactly know the reason for that, but I think it's just to provide more clarity in two different things. One is the compilation of your circuit into a general R1CS, and this is the actual prover stage where it generate proof based on the given input. So yeah, and then we can then use this anywhere, right? We can verify a proof. And if you put in the previous value, like 380 and something, because, so this is a proof, you see, it's multiple things. And let's say if we just put in some random value, it will just fail because obviously, but if you put the correct values, yeah, in this case, it's correct, right? We can put in any values here. And this, like when I generate proof here, it's essentially the proof stage where I give it some input and it actually executes it based on, like, executes it on the R1CS or on the circuit itself and generate an actual proof. If we don't talk about the generation of the actual proof itself, it will be just, well, the only difference here is that in the setup phase, the compiler is using the inputs you give it to generate the R1CS or the graph or the algebraic circuit. But in a prover stage, it's not, well, it's more towards now with what the compiler has produced, you are executing, or the compiler is executing your code itself. And that doesn't make sense from a programming standpoint, but you're actually executing it instead of generating. Your goal is no longer generating R1CS. In the setup phase, your goal is to generate an R1CS. In your prover phase, your goal is to execute or to run, yeah, run it with some input. I think that's what I've understood from this. That's why I think they separate it out just to provide this clarity, specifically for Circom and a lot of circuit language out there. Anyways, okay, yeah, good question by the way. Anyways, okay, let's get into this section. Any questions? Common programming concept, primitive types, base field type, control flow, conditional loops, binary field, cryptography primitives, twisted Albert curves. I'll go through a little bit, like speed run through this. So yeah, if you are a programmer, most of this you probably know. Yeah, primitive type just means types that the language support. So for a circuit programming language or for a circuit language, your primitive types would be more towards things that the field or that the field support, that your field support, right? That your curve support, or right, depending on which is it. So strings is probably very hard to support, but yeah, you can technically convert string into some field element that works anyways. Yeah, base field, what's the base field type? So yeah, the base field needs to have addition and multiplication, and this needs to work, right? Yeah, this is how it's implemented. Shows this. Yeah, it converts it into like this, something like this. This essentially is addition, right? Yeah. So your addition circuit, so they might be also a circuit itself, your addition operation. And this addition operation, you can do some elliptic curve operation, some, yeah, group operation as well. But yeah, generally your programming language, like your circuit programming language will also have this, and they are usually implemented via either other gates. So in this case, if we implemented like this, but no, this is basic ops. But it might be implemented in other gates as well itself, or just part of the, well, well, one of the integrated thing that the compiler knows how to convert into. Yeah, so here it shows that, yeah, maybe your add and multiplication circuit can be, so add and multiplication operation can just be another circuit, right? Yeah. subtraction constraint system. So it talks about how subtraction can be done in this case. And it's a circuit essentially. So it's basically saying that all of these operations, you can basically treat them as a new circuit that is written. Um, yeah, that's also funny enough, a lot of the current latest VMs also do the same thing. They basically have some operations, some primitive operation implemented via a circuit and then just include it by default. So you can use it very easy. Inversion constraint, so inverse, um, yeah, how inverse is implemented in a circuit. In this case, it can be defined like this. But in this case, because um, well, because you can't do inverse in the language, what you do instead is it yeah. So real world program like real world compilers they do have a way of doing inverse. I don't think Circom has, but I think the more modern ones you can very easily do things like this. But you don't really use inverse that much, I don't think. I might be wrong. Anyways, so in this example itself, this paper example itself, we were just basically defining our inverse compiler to be a inverse circuit, sorry, to be a circuit that compares two inputs. That when multiplied together will become one. Yeah, that's essentially it. Because in this paper example, we can't compute, or in this paper compiler, we can't compute the inverse. Yeah, so real-world compilers usually provide a gadget or function to abstract over this circuit, and those functions compute the inverse x to the power of -1 as their witness generation process. Division, so this shows how division at circuit might look like, which is something like this. Again, use of inverse, remember. Yeah, so addition and multiplication is pretty simple to do in ZK because of this, because it's pretty easy to do multiplication and addition in field arithmetic. And you can see it here as well. Boolean 0 and 1. Yeah. Boolean constraint system can be something like this as well. So yeah, any questions to ask? How n might be implemented. So this goes through how each of the types can be implemented as a circuit in a very simple example, like the paper, pen and paper compiler or language, compiler language, yes. Sorry, circuit language. My brain's not working today. Yeah. So let's go a little bit into something more interesting. So arrays. So array can be implemented, but you cannot implement lists. So actually, if you look down, we just go down. So this is just unsigned integer time, which means that you cannot go negative. Yeah. Um, okay. Anyway, so arrays and control flow, in control flow, loops especially, even conditional here. So in a circuit language, your program needs to be deterministic. That's why we can have arrays as long as you need to define the length of the array at the compile time, essentially. Yeah. So yeah, here it defines like, array, we define this type function, which is syntactic trigger to show many element essentially, because array is just a bunch of elements, but you can very easily access them via an index. Yeah. So yeah, arrays is possible to implement, and you can just define it like, you do first index, you return 1, and so on and so forth. For your control flow, conditional, it's pretty hard to implement conditional if it's not deterministic. So if you implement conditional, it has to be deterministic. So yeah. So loops as well, you can't have loops that go forever. You need loops that is deterministic in the sense that it cannot be determined during dynamically. It needs to be known during compile time. So your loop, how many times your loop runs should be immediately known um before you even provide any input. Yeah, because yeah, R1 CS and algebraic circuit generally can't really have undefined behavior. Of course, well, you can make it so that you can make it so that it's possible to write things like this, but you have to, when you compile it down to R1CS, you have to do some checks to ensure that some bounds are put on this. Or else, yeah, this doesn't make sense, or you can't really generate a valid R1CS. Anyways, okay. So binary field a representation here. Any questions on this? So can represent your yeah, can represent your fields that you work on in binary as well, and you can represent in the bit string. And yeah, so cryptographic primitives, which sometimes you need. So for example, hashing and specific curve operations. You can also write circuit to constrain. So in this case, it's essentially showing you, let's say for the twisted Edwards curve, can you represent them in circuits? Yes, you can. It looks like this. And the R1CS is like this. Yeah, that's essentially it. Actually, this chapter is all about how, when we're writing a circuit compiler, or like when trying to make it so that it's like make a circuit language, I suppose. How does it look? I guess practically, how does it look? To write a circuit. Yeah, you can. I mean, if you have any questions on this, we can go into detail. But for now, I think that's all that I have for today. Any questions before we end today's session? Do ZK-VMs have their own circuit compilers? Um, so well, ZK-VM itself, well, they work on okay, let's talk about RISC-based ZK-VMs, okay? So RISC-based ZK-VM, they work on the RISC opcode, and when they go through the opcode, technically what they are doing is they are compiling what the opcode does down into their own constraint system. It's not R1CS. Most are using Fry, I think. But essentially it's similar to R1CS. Yeah, when they are processing, like let's say RISC 0, when they are processing your program, your Rust program, right? First of all, your Rust program gets compiled down into RISC-V, and then RISC-V opcode, and then the ZKVM actually looks at the RISC-V opcode and then compile it down into their own constraint system. I believe it's if I'm not wrong, it should be AIR, algebraic intermediate representation. In their case, it's not R1CS. But yes, they do compile it. I would say they themselves are the compiler. So a ZKVM is a compiler. So they don't compile Rust into a circuit. They compile they compile the opcode of the Rust code into a circuit, or in this case, into more accurately, into their own constraint system, which they can then use in order to generate proof. Yep. Any more questions? Good question, by the way. I'll take that as a no. If you have any more questions, DM me, ask in the group, and whatnot. But in the meantime, thank you very much for today, and I hope all of you have a great night. Bye-bye.